This is AP Calculus, Unit 11, Lesson 4, and we are on our last standard, Standard X, which is volumes. So today's title is Basic Volumes of Revolution. Where are we in the unit? We are almost done. We're on our second to last lesson for the entire year. And then tomorrow we do Advanced Volumes of Revolution. And if you know anything about calculus and you're watching this video, we're talking about the washer method today. So we have these two functions. We should label these. We should label the top one f of x. We can label the bottom one. We're going to use this space right here. So let's say g of x is equal to this function. We can label it with an arrow. So what I'm going to do is I have this region, and you can say that, okay, this region, don't do this in your notes, but this region has an area right here. And what I'm going to do with this area is I'm going to sweep that area all around the x-axis. Again, this is our x-axis right here. So what happens when I do that? And this is where we have to have some artistic talent. Let me do my best. So if I sweep around that area, it's going to look like this. There it is. It's getting swept around. And maybe I should just come down here. Comes down here, gets swept around. And I have my red g of x on the inside. I have my blue f of x still on the outside. And it gets swept around all the way 360 degrees. So I guess technically this is a kind of like a donut shape. I tried. I guess I could do a little bit better. It's a donut shape, and it comes all the way out the back as well.
Oh, what do you mean by swept around?
So think about, and I can't capture this in the notes or on the computer, but if I have some axis that I'm revolving around, you have some area that you are taking that area and pretend that you can. What's a good way of saying it? You can capture the moment of the area. If I'm going all the way around, that area is turning it into volume as I sweep around the x-axis. So if I had that shape and I sweep it around the x-axis, it is suddenly turned into the volume of, think of like a donut, a torus.
So it's a reflection?
So it's not a reflection because technically all of this is an area. So let's see if I can draw what's happening out here to the side. So I have all of this, and it's like a donut. Each of these slices right here was a slice of area. Each of these slices right here was a slice of area on this donut.
So it's like a tall donut.
This is a donut flipped on its side, exactly. And each of these one slices was the area that we started with, f of x minus g of x. Can we see that?
Oh, wait, so it's a donut flipped on its side.
Yeah, so this is the whole of the donut over there.
Oh, I
All right.
Oh.
So what I want to do is talk about what happens when I do a cross section. So let's get rid of that donut shape. So what happens if I do a cross section? So my cross section, let's cut it like this. What do I see in that cross section? So we can label this area over here cross section. I don't know, I did a G. Cross section. And girls, you haven't seen the notes yet, but I talked about cross sections on Friday, and it's just a way of visualizing volume. So the cross section will look like this. It will have the outside, and it will have, I guess if I was drawing to scale, it would look like this, but I'm not going to draw it to scale. I'm going to draw the inside like this. And then there's some empty area because all of this area right here is empty. That's a giant hole. So our hole should have looked more like this. I'm trying. That's our giant hole. Well, technically, I guess the hole would be the entire thing. Anyway, it's difficult to draw in the third dimension. I need practice. But this is the cross section. If I slice it like this, this is what that one slice looks like. Can we tell what the area of that slice is? Using geometry, if I told you the different radii, I know the radius here, I know the radius here, would you be able to tell me the area? This is a yes-no question. Yeah, how would you do that?
Subtracting.
Yeah, you subtract. So you have that blue area, the circle, and then the red area, the circle. These should be making perfect circles, and you can subtract them. So that's what I want to do right here. Let's go down here to this next line and say how to find the area of that washer. Find area of washer. So the cross section here made a washer. Are we familiar with what a washer looks like?
I don't know.
Okay, so I can do a Google search here to show you what a real washer looks like. These are washers. These things right here.
Okay, washing machine.
Yeah, so they're.
So basically, it just looks like a washing machine.
So it basically looks like a washing machine, sure. No. Okay, so how do I find the area of that washer? So let's redraw that washer down here. So I have actually I have technology. What am I doing? I can make a perfect washer. So we have the outside area here, and we have the inside circle here.
I can draw that.
And I'm going to move this so that they look better. Right about there. So we know that to find the area here, this is going to be equal to, I take the area of that blue circle, and I can just copy paste. Having technology is lovely. I'm going to have the area of the blue circle, and I'm going to subtract the area of the red circle.
There goes Kayla going in.
And we know what those different radii are, because how do I get, let's try to visualize this. This radius from the center of the circle to the circumference, to the outside part of the circle. What is that radius? And we need to refer back to this line over here. This graph up here. This radius represents what line? How could I draw a line somewhere on this graph to represent this radius of the circle? It is f of x. It's just the height, right? So this height right here is the radius of that circle. And I can think about that, oh, when I take the cross section, yeah, that makes sense. It's the radius of the circle. So I can label that, I'll just, normally in calculus books, they say capital R, big radius. And to find that little radius, so I can come back here, let's do red. This radius right here, we'll say that's going to be our lowercase r. How do I find that on the graph? It's g of x. It's just this height right here. It's g of x. Perfect. So I'm going to continue on to the next slide, but I'm going to, oh, no, I don't want to grab that. I'm going to grab all of this to copy paste onto the next slide.
My drawing's so
bad. And let's do our calculation. So our equation is going to look like this. So this area here, we can just say that that area is going to be equal to, well, what's the area of a circle again? Formula, girls? So it's going to be pi capital R squared minus pi lowercase r squared. And we know from Joy that capital R is just this length of f of x. So we can substitute in for capital R, we'll say f of x. So f of x, and it's all of f of x. I'm going to do double parentheses squared minus pi times, and this is g of x over here. So g of x, I guess I should have color coded this. G of x, that quantity squared. I'm going to pause here to make sure we all understand what's going on here. We're trying to find this area right here. To find that area, we took the big circle minus the small circle. We know what the radius is here because, really referring back to the problem, this was a cross section, so we're taking f of x represents capital R, g of x represents lowercase r. Do we have questions up to this point?
No.
Okay. So let's go ahead and factor out a pi. Both these have pi in it, so I'm going to bring pi to the outside, and this is going to be just f of x squared minus g of x squared on the inside. F of x, all that quantity squared, minus g of x, all of that quantity squared. I do parentheses around this because you might have a negative, so I have to be careful about that.
You couldn't just like. Never mind.
You could calculate these individually and multiply pi through them. This is the shortcut. You factor out pi, and our formula, I mean, this guy is pretty key. That should be in our summary. This thing is our formula that we need. But more simply, it is this.
Wait, what should be in our summary?
This equation right here is pretty important. I give it a star. And also this, that the area of a slice, when we're doing this type of method, when we're rotating it around the x-axis, sometimes you can be rotating this around the y-axis in very rare cases, but usually it's around the x-axis, is going to be this. It's going to be pi times the top equation minus, or the top equation squared minus the bottom equation squared. All right, so I have the area. How do we move to our final step to volume? And I need to make a new slide here.
Is this our last slide?
This is our last slide. There's not very much on this slide.
To multiply by the height?
Multiply by height? And what do you mean by height? What on our picture over here do you mean by height?
The cross section.
Yeah, so if you're thinking about it like this, I think this is what you're thinking. If you treat this as a volume, the height of that washer, what is that height of the washer? Does anyone know? I guess only Joy would know because she was here for the notes. We had a very specific height here. You want to take a guess, Joy, or you want me to give it to you?
Yeah.
This height here is dx. We can change that height of the washer to be whatever we want. So when we come over here to finally get to volume, and this is also pretty important here, to finally get to volume of a slice, of just one slice, that's going to be equal to the same thing. It's going to be, and this isn't important, so I'm doing it in blue. Same thing is going to be pi times, we have our f of x quantity squared minus our g of x. I should be doing quantity squared. But now we're going to multiply by height. Height was dx. So this thing now represents, we had this washer here. I'm just drawing the picture again if we need it. And then we needed to have some height on there. That was our dx right here. That was the height of that washer. Volume of one slice. But now how do we find the volume? Oh, sorry, go for it.
Okay, so dx gives you the height?
Dx will give you the height of one washer. And you can change dx to be whatever you want. How much are you changing in x? Remember, dx represents delta x. That's how we used to call it, the change in x. We can change this height to be 0.1, 0.01, 0.001. You can make this almost 0. You can say 0.000000001. That could be your height. The number of washers that you need to fill in this shape will change depending on what your dx is. And this is, again, is review from last lesson. How do we count up all of those washers? How do we sum all of those washers? What is the symbol that we use to sum an infinite number of washers?
Infinity.
No. So this is the volume of all slices. We're taking an infinite number of slices, and we're taking these slices to be almost infinitely thin. Volume of all slices. Do you remember, Joy?
Sort of.
This is going to be the integral of this function. Integral of pi, and we have to write it again. You'll write it so many times, hopefully you'll remember f of x, all of that quantity squared minus g of x, quantity squared, d of x.
So each time we're just adding a step?
Each time we're adding a step, and here's your final formula. This is the most important thing I can give you today. I'll give this another star.
Give it 2 stars.
2 stars, sure. I like it. So the volume of all slices, all I'm going to do from our last step is I'm going to factor out a pi, because whenever you have a constant, you can put that constant in front of the integral. So it's going to be pi, the integral from wherever you're going, from a to b. And I'll talk about a and b in a sec, what those actually mean, but let's go ahead and recopy all this down. It's going to be
Is this formula for the volume of all slices or the volume of one slice?
volume of all slices. This is the volume of this entire object, this torus, this donut that I'm finding.
Okay.
Well, it's not really a torus. It looks like a kind of a donut shape. F of x quantity squared minus g of x, all of that quantity squared, end bracket, d of x. And just to add on a note here, I'm still going to do this in red. This thing was our capital R. That was the top. This thing was our lowercase r, so it's lowercase r squared, and that was our bottom.
And then, so for the area ones, was that final equation you give us the area of the whole thing or area of one slice?
The area of one slice.
And then the equation above it with the star, is that area of all slices?
So that was also the area of one slice. Both of these we're talking about area. Everything on this slide was just area.
Okay.
Once we move from area, it's easy to move from area to volume. And again, this is really heavily based off of our last lesson yesterday, or on Friday. Perfect. So that is our main double star formula. We know how to find area whenever I revolve around an axis. On Friday, we found how to find volume when we do a cross section of a square. Today, we're just revolving, making everything circular. And then tomorrow, we're also going to be doing another type of revolution, but it's a little bit harder. All right, that's all we have for the notes. Go ahead and do your summaries. All right, so our first example problem is going to be number 3 on the homework. We're skipping 1 and 2 because those are pretty straightforward if you know how to do number 3. Okay, so number 3, it gives you too much information, and that's because there's a part A to find R, and there's probably a part B that we're not doing to find S. So don't worry about S for this problem, we're just finding R. And we know what f of x is, that's the one that bounds R, so we're really only working with our f of x here. So we're trying to find the volume of the solid generated when we're revolving around the x-axis. So let's set this up. We know that our volume for R, it's not actually R, so it should be V, because R is the area. So V is going to be equal to, and then we're just using our formula back here. So it's going to be pi times this integral. So it's going to be pi times this integral from A to B. So this is something that I forgot to go through in the lesson, but what are A and B? A and B in this problem is just wherever this point starts, that's A. Wherever this x coordinate is, that's B. It's always just talking about the normal area function, and then the volume comes from doing dx. So A and B, just think about your normal area between two curves. So that means in this problem, I need to find the area between wherever R touches the x-axis, because we're revolving around the x-axis. So here and here. I know this point is going to be 0. How do I find this point using the calculator? Or better yet, there's a way to do it even faster without doing the calculator. Can anyone see it, girls? Set f of x equal to 0. Perfect. So I'm saying 0 is equal to 4x squared minus x cubed. Factor the right-hand side. So 0 is going to be equal to 4. Well, actually, I'm going to factor out an x squared. So x squared, 4 minus x.
Mr. Snell, do you think this is faster than using your calculator?
I do, because you should be able to do this in your head and do it like in a second. If not, you can just use your calculator. I'll show you both ways. Therefore, x is equal to what and what?
Positive
4 and
0.
0. Yeah, those are the two places where it intersects the x-axis. So we know that this is 0 and this is 4. Let's say you didn't want to do this, or maybe you had an equation over here that was really unruly and I didn't know where this intersected the x-axis. On our calculators, there is a way to do it. So if we graph this function, so our function was 4x squared minus x cubed, and that's going to be set between 0 and we'll just say we didn't know where it intersected, so we just said 5. We hit zoom 0. Ooh, that'll make it too much in the negative direction. And we're saying, oh, how do I find that point? You just do second trace. We're trying to find the 0, so you hit 2, and you say the left boundary, we can say 3. Between 3 and 5, we'll guess 4, so 3, 5, and our guess is 4. And it would tell us, yeah, it is actually exactly at 4. So that's the way to do it with the calculator. But we know it's at 4, so now we know what our bounds are for our integral. Our bounds are from 0 to 4. Those are the bounds of this area of R. Then from here on out, we're just using our formula that we need to memorize. So it's going to be the top squared minus the bottom squared. So top squared, well, we only have a top. We don't have any bottom, which is really nice. So the top here is f of x. So I could write all of this out, but I'm just going to be lazy in my notation. So it's f of x, all of that squared. And technically there's no function. Our function is our x-axis, so it's minus 0 squared dx. All right, time to plug that into the calculator.
So when there's no g of x, you just put 0?
Yeah, there's no g of x. So you can just leave it blank, or you can say minus 0 squared if you want to be very formal about it, I guess. So time to do this on our calculator. I already have f of x in my y equals. Sometimes you'll have to enter it in manually, but let's go through this. So this is going to be second pi, so our second to the power, so pi times this integral. So math 9, the integral between 0, or so it's going to be y1 for me, var is right, enter, enter. If you want to instead do all of this squared, so you could do 4x squared minus x cubed and then do parentheses around that squared, you could do it here. Or you could just do y1 squared. Either way will work. If you got to graph it, then this way is faster. So y1, make sure you remember the square here, and that is going to be with respect to x from 0 to 4.
Clear.
And when I do that, I get 490.208. So 490.208. And remember, this is a number that represents volume. It's as if I had this thing and it was being rotated around and making kind of a donut shape is the best word that I have to describe it, but it comes out into the third dimension and gets rotated around this x-axis.
So what's your units for volume? Wait.
It's something, it would just, if we don't have units, it'd be units cubed. If it was centimeters, it'd be centimeters cubed. Inches, inches cubed. I'm just saying units cubed to be general. Question, Kaylin?
Can you go over how you found that number again? Because I did not get that.
Did you multiply by pi already?
Yeah.
All right, so pi.
Where do I want?
Oh, that's why.
Yeah, so that will be probably the most common error here.
Okay.
So,
All right,
y1
so
squared, comma, x, comma, 0, comma, 4, do that, 3, 5. Okay, I got it now.
perfect. Let's move on to number 4 on the back. All right, so for number 4, the first thing that we want to know is which one is on top, which one is on the bottom. We have two equations. So it says it's bounded above by this one and below by this one. So that means this one is going to be the top, and this one is going to be the bottom. So our integral for our volume is going to be pi times the integral from a to b, and we don't know where a and b are, so we'll have to come back and find those. But it's going to be our top squared, so it's going to be 20 over 1 plus x squared, all of that quantity squared minus 2 quantity squared, and then all of that is going to be multiplied by our dx. But we don't know where our bounds are, so let's go ahead and find those. Our bounds are wherever these two functions intersect, so we basically need to do this. 2 is equal to, yes?
How do you know that that one's the top and that one's the bottom?
It says it's bounded above by this graph, so above
And below.
and below.
Okay.
Yeah, exactly. Good question. Yeah, so we basically need to set 2 equal to this, so 20 over 1 plus x squared. So there are two ways to do this problem. You can either solve this algebraically, which probably takes a little bit longer if you're not used to solving these. And the second way is to graph these two equations. You graph this function, and you can graph the second function. You can either subtract them or just graph them individually. If you graph them individually, you're looking for an intersection point. If you graph the subtraction, you're looking for where it's equal to 0. All right, so there's 3 ways that I just said. Which way would we like to go through this one? Algebraic. So if I do this algebraically, this is the same thing as 2 over 1. Cross multiply, I'm left with 2 plus 2x squared is equal to 20. I subtract 2 and then divide by 2. So this is going to be x squared is going to be equal to 9. X is going to be therefore equal to plus or minus what? 3. So our volume is going to be between -3 and +3. And then from there, we just need to plug this into our calculator. So, calculator. And I'm going to do this without entering anything into my y1 function. I'll even clear that so I don't make that mistake. So again, this is going to be pi times math 9, this integral, and I'll have to be really careful with my parentheses here. So I need parentheses around this first function in order to have the square. So I'm going to set up that parenthesis now. It's going to be 20 divided by, and now I'm going to set up parentheses for the denominator. So there's a lot of parentheses here. I'm setting up parentheses around 1 plus x squared. So it's parentheses 1 plus x squared, bless you, 1 plus x squared. I'm ending the parentheses for the denominator. And now I'm going to end the parentheses for the entire function. So it's double end parentheses, and this is going to be squared. So what I've just done now is this function squared minus 4. And I'm going to do comma with respect to x, comma from -3, comma to 3, and I hit enter. Oh boy, it's taking its time. And I get this function, or this number, 1,871, so this is approximately equal to 1,871.1 190. Even if it's a 0 here, I prefer us to leave it there. It lets me know that you did indeed round to 3 decimal places, to the 10,000ths place. No, thousandths place, sorry. 10,000 would have been another 0.
Do we need units?
If it gave us units in the question, then yes, it didn't, so you can just leave this as a number. If you want to be really specific because you like being extra correct, you can say units cubed. Because you know it's volume.
Are they always going to tell you what's the top and the bottom so that you know, or is there?
Sometimes they won't, yeah. And in that case, you'll have to graph them on your graphing calculator.
Oh, I just see which one.
And as a hint, the way that your graphing calculator works is it graphs these functions in order. So if it's making the first line, that's going to be your y1 function. And so if it's making the second line, that's your y2 function. All right, perfect. And is there any question that people want to see right now?
Number 6.
So this was 4, 5, 6. Yeah, 6 and 7 are both kind of tricky. Let's take a look at number 6. All right, so we're going on to this problem instead. So number 5, let R be bounded by x-axis and this graph at the line x equals 4. All right, so finding the volume generated around the x-axis. So it always helps me to visualize these, to just do a quick sketch. So I'm going to do a sketch on the side. So y equals square root of x, it looks like this. It comes out. Line x equals 4 means I'll have a line right here at 4. And I'm bounding this also by the x-axis, so this x-axis right here. So I'm looking at this shape right here, and it's going to be rotated around the x-axis.
So every time square root of x looks like that?
Yep.
Like that's something we should memorize?
Yes, you should definitely memorize that.
Oh.
I'll be making a sheet, I guess, in the future, hopefully today or tomorrow, showing you the basic graphs that you have to have memorized, just their basic shapes.
Yeah, because like there are certain things that I'm just kind of like
Like
that
on
I
that
need to, like,
homework
know
before?
for the.
Right.
That like didn't have the equations on it?
Yeah, maybe that should be a prerequisite before doing calculus. That should be like in unit 0. All right, so first thing first, what are our bounds here?
Oh yeah. From 0 to 4.
Careful. Yeah, so 0 to 4. Perfect.
Do we need to write like v equals?
If you want to be exact, yeah, you can say that. V equals, volume is equal to this, so pi times this.
You have to write this from the working out.
Yeah, that wouldn't be marked down.
Okay.
And what's our top function?
Square root of x.
Square root of x, and that's going to be quantity squared, and that's going to be subtracting what squared?
4 squared.
Nope. Look at our graph. What's the function that goes underneath this function? Good guess. 4 was this line right here. The bottom function.
0.
0.
Oh, yeah, because I was really confused of like how 4 was like underneath it.
Perfect. All right, so when we calculate this, we can probably do this by hand. I don't even think we need our calculator for this one. Because this is going to be just x, so this problem turns into pi integral between 0 and 4, oh, we have 5 more minutes left, of x dx. We can do that by hand, yeah?
Yeah.
Okay, so if we do that, then this is going to become integral antiderivative of x is what?
4.
X squared
X.
divided by 2.
Yep, so this is going to be pi x squared over 2 from 0 to 4, evaluation bar. When I plug in 0, I get nothing, so it's just going to be pi, and I plug in 4. 4 squared is 16, divided by 2 is 8, so it's really 8 pi.
That's the answer.
That's the answer for the volume. That's only A, yeah. B is the hard part. So the vertical line x equals k divides the region R into 2 regions such that those 2 regions have the same volume when rotated around the x-axis. We need to find the value of k. So what is happening here? On this graph, they're saying I can find some line like this at value k such that this volume and this volume are the same when I rotate them. Where is that value of k?
2 would be the midpoint. No, scratch that. Never mind.
So
1.
I don't think we can... Well, Joy, what's your logic behind saying that k is equal to 2?
He said that they would be equal to each other, but we wouldn't.
They wouldn't
Because
be.
like the line on top is going up, so it has to be like.
Yeah, so here's the key part. We don't really need to look at volume. Because if these have the same area, then they're obviously going to have the same volume when we rotate them, because all we're doing is we're plugging it into the same formula for the area of a circle, pi r squared.
Okay.
So what we really need to say is, where do these two have similar or the same areas? Any ideas?
No.
Finding a single slice.
So it doesn't have to do with slicing, because slicing has to do with volume. We're just talking about areas here. All right, so we can set this up algebraically. Here we go. I'm not quite sure how to solve this either, so I'm just going to kind of go for what my intuition says. My intuition says make two separate integrals. This is from 0 to k and from k to 4, and set those two integrals equal to each other.
That does seem fun. It's just like I was expecting
Well, thank
a
you.
grand, like,
I,
answer.
that makes me feel happy. So this is going to be from 0 to k
I'm glad.
of this function.
Oh.
Sincerely.
This function is square root of x dx. That needs to be set equal to the value from k to 4 of square root of x dx.
You're like really tired, like you're saying these crazy things.
Oh, yeah.
All right, remember, square root of x can be written how? Oh shoot, we're out of here. X to the power of 1/2.
I mean, that's what I meant.
And then when I take the integral, I'll be taking this, that's going to be x to the 3/2. And then divide by 3/2, so that's 2/3. And that's evaluation bar between 0 and k. That needs to be set equal to 2/3 x to the 3/2 evaluation bar from k to 4. Evaluate both of these, solve for k, that's your answer. And that is all the time I have left.
It's a whole.
But